Well, hi to everyone and welcome to this Danesco webinar. Okay, right now I'd like to introduce today's presenters. With us today we have Bill DeRocher. Bill has been Vice President of Business Development for Dynisco the past 4 years and is responsible for the market development and growth of Dynisco's key strategic initiatives. With 30 years of focus in the plastics industry, Bill is a proven leader with extensive management and global business experience. He has held a variety of roles including mechanical engineer, product manager, director of aftermarket and customer service, sales manager, and VP of international sales. His experience has garnered a plethora of knowledge ranging from product development to international sales. Bill also holds a Master's of Science in Project Management from Boston University and a bachelor's degree in Manufacturing Management with a Mechanical Engineering minor from Roger Williams University. Okay, next up we have John Cazzotti. John is currently the Director of Engineering for Danesco in Franklin, Massachusetts, and is responsible for Danesco's engineering at their Franklin, Mass., Akron, Ohio, and Shanghai, China facilities. John has had various roles in engineering, manufacturing, and product management over his 25-year career at Danesco. Most recently, he led efforts to create Vertex, a patented pressure sensor based on a disruptive technology that will replace Danesco's core melt pressure technology. Danesco received several Innovation and Technology Awards for the new technology and process, including the prestigious American Business Award, where they were recognized with a Gold Stevie Award as an Innovative New Product of the Year. They also received a Silver Award in the category of Most Innovative Tech Company of the Year. In addition, Flow Control magazine recognized Vertex with its 2013 Innovation Award. Also with us today is John Biagioni. John has been the president of Danesco for the last 4 years. He has also led 2 other Roper companies, Viatran and DJ Instruments. He started with Danesco over 10 years ago as vice president of supply chain and operations, covering 4 domestic and 3 international facilities, and was the driving force behind Lean, TCO, and DFMA methodologies within those organizations. Now, prior to that, John held the position of General Manager of Manufacturing for the Measurement and Instrumentation Division for Invensys Process Systems, a Foxborough company. John also held many supply chain roles including Group Commodity Manager, Engineering Purchasing Manager, and Manager of Strategic Non-Production Purchasing at EMC Corporation. There he achieved over $150 million in negotiated cost savings 3 years in a row and led purchasing re-engineering efforts that applied various sourcing tool sets, including low-cost geography sourcing, clean sheets, and linear performance pricing. Now, while at EMC, he had strategic responsibility for budgets from $600 million to $1.5 billion in spending. John holds a bachelor's degree in economics from the University of Rhode Island and a Master's of Science in Operations and Information Technology from Worcester Polytechnic Institute. Now, John will be joining us at the end of this webinar and will be available to answer any questions that you may have. So John, Bill, and John, welcome to today's event. And with that, I think I'll pass things along to Bill to get things started. So Bill, go right ahead.
Hello, and thank you for joining our webinar, Simplified Rheology for the Masses, a Technical Discussion. My name is Bill DeRocher, and I am the Vice President of Business Development for Danesco. Danesco provides tools and services for the polymer industry, allowing our customers a window into the process. Today's customers need more than a product. There is a need for information that will allow our customers to validate their process, ensuring the products they make meet or exceed their specifications. Danesco allows them to do just that, whether that process is local or in various locations around the world. Our diverse sensing and polymer test platform deliver the most accurate information available in the market today for the measurement of pressure, temperature, and polymer rheology. Danesco provides our customers the ability to correlate the data derived from the pilot or laboratory environments with online production 24 hours a day. This data allows for immediate response and adjustment to critical parameters to ensure that products meet the design specifications continuously. The goal of this webinar today is to explain the technical aspects of correlating laboratory measurements to production, and how with today's technology, Danesco has developed a system that will allow all processes an easy way to implement the system into their production environment. The topics we're going to cover today are market drivers and importance of rheology testing today, the science behind melt index determined at the extruder. We're going to go through an example of an installation, and then we're going to take questions at the end. As you may recall from our first webinar on rheology for the masses, I want to start off by reviewing the market drivers that are impacting the need for rheologic testing for today's processors. We feel that today's polymer market is in the midst of a convergence of events that will create sustainable growth requiring processors to implement additional quality control methods for validating polymer. We have grouped these into three pillars that address specific growths in each area of the market. First is sustainability initiatives. Sustainability initiatives today across the globe have moved past the traditional economic advantage of reusing recycled material. Sustainability today addresses all aspects of the product life cycle. It's not just about reducing cost by using your scrap, it's about the zero waste zone, repurposing all plastic items produced with the goal of zero landfilling. The sustainability pillar requires all processes to better understand rheology. Regrinding allows for seamless integration into their process without affecting quality. Second is the global reshoring, right-shoring initiatives. Today we live in a truly global market. Most companies are affected by moving plants from one region of the world to another for a variety of reasons. These range from cost savings, being closer proximity to their customers and markets, and addressing quality concerns. With production facilities around the world, now more than ever it is critical to ensure your quality is maintained, regardless of the supply of the polymer, location in the world, and use of recycled products. Danesco's goal of supplying a window into the process is the first step to addressing consistency with one of the largest expenses for a plastics processor, material. The third pillar is around growth and expansion in the polymer industry by utilizing shale gas to manufacture polymers. With larger polymer producing being implemented globally along with the secondary operations being put in around these facilities, the need for automated and more complete polymer rheological tools will grow. At Dynisco, we recognize this trend, and we're producing tools that are focused in each area of this market, from advanced, extremely high outputs of the resin producer to the compounding or recycling facility with just a single extruder, and every size in between. We have developed products that are designed to bring rheology to the masses. Before I move on, I want to quickly introduce you to Danesco's line of polymer test equipment. From left to right, you'll see the LCR capillary rheometer, which tests and simulates polymer at varying pressures, temperatures, and LOD ratios. The data generated with this instrument is a benchmark for evaluating polymers in the academic world, as well as production environments. Next is the melt flow indexer, or plastometer. It's used for quality control and verification of polymers to ASTM and ISO standards. The next is our benchtop compounding line, the LME, TUS, and LEC. This is used for small batch compounding of specialty polymers. Our newest additions to these lines are the Mini-Gren. It's a small compact granulator that reprocesses material to be put into our melt flow indexer or capillary rheometer, and our Polyclean unit, which comes in 3 different sizes that will easily clean up lab dyes and orifices, as well as production components like breaker plates, nozzles, and even pressure transducers utilizing a special fixture. Lastly, we have Dynisco's online rheometers, the Visco indicator, Visco sensor, and the CMR4. These are used for real-time rheological data for online purposes, correlating the data between the lab and the production environments. Plastics processes have to constantly navigate through the daily circle shown on this slide. There's a constant tug of war between increasing productivity, implementing corporate and regulatory sustainability programs, and saving money, all while maintaining quality. In most cases, when this struggle occurs, something gives. Focus on productivity and cost, quality may suffer. Focus on increased recycled material, cost may improve, but it also may impact quality and productivity. Our focus today is to give processes one less thing to worry about, specifically making sure the polymer you are using is of proper specification. By ensuring your polymer rheology is correct, not only the virgin material, but when combined with other recycled polymers, you will eliminate the area where it's most difficult to identify problems. Polymer in general is a blind item. Looking at repelletized polymer, you cannot visually notice a characteristic that could impact final quality of the part. In the next couple of slides, we will review best practices on where, why, and how to measure the specifics. After this short review, Dynisco's Director of Engineering, John Cazzati, will go into technical aspects and mathematics of the polymer rheology and what inputs affect the polymer stability. It is important to realize that a little bit of time up front, combined with the validation in the process, will minimize the investigation when parts produced fail prematurely or do not meet desired parameters. Most importantly, your customers will be assured that your process is validated and the quality will be maintained. Why do we need to measure polymer specifications? First, you want to ensure what you are receiving from a supplier meets what you bought before it enters your process. Polymer tolerance can vary greatly between batch to batch and suppliers to supplier. It is important you understand what works best for your product. The engineers chose a specific polymer for a reason. You want to make sure it meets the specifications outlined in the data sheets. Second, are the process settings in your production operation set up properly? This is important on two fronts. It ensures the polymer does not degrade and affect quality of your product. It also helps you with the recycle of your scrap. The correct process settings and verifications will minimize degradation. We'll talk about this more in a few slides. Recycling mandates of many corporations or industries require a certain percentage of recycled content. It is best that you use or purchase material that is closest to your virgin specifications to maintain quality. If regrind is being introduced into your system, you need to decide what's the best maximum percentage of regrind you can use without impacting your quality. When interviewing molders or extrusion shops, we have found that many plants evaluate percentage of regrind based on a few parameters. They include initial lab studies done when the equipment was installed that define how many times regrind should be used, corporate, government, or industry regulations on use of recycled material in the product, and individual plant historical best practices. These strategies are fine as a guideline, but it brings up issues on how you monitor how many times a piece of regrind has been through the process, as well as consistency of the polymer regrind. The material tested may have different temperature settings, variations in fillers, and they may not be specific to the regrind that was originally tested. If you perform these simple analysis, you can dial the proper blend ratio at the time of production to ensure quality and maximize profits per part. When material is not properly vetted, there will be consequences in your end product. If melt flow isn't a specification, your part may be too brittle or too soft. This can cause defects that will show up in your end product. The problem with this will be increased scrap, or even worse, you may hear well after the shipment of quality issues in the field, which could lead to warranty claims or lost customers. Now that we have quickly reviewed the market drivers and importance of rheology to the plastics processor, I would like to introduce Danesco's Director of Engineering, John Cazzati, who will go through the technical aspects of polymer rheology and how we can use this information to correlate values developed in the lab to production 24/7. Thank you.
Thank you, Bill. I will cover the science behind melt index determined at the extruder. This slide shows a list of products from Dynisco that measure rheology on the extruder. With these products, compounders and resin suppliers do not have to wait for their lab test results on production samples every few hours. They can maintain almost real-time control of product quality with an online rheometer. Online rheometers process a side stream of melt diverted from the extruder. After testing, the melt is either discarded or returned to the extruder. This equipment is not new. Dynisco has offered FCR and CMR for decades. Traditionally, the hurdle for this equipment to overcome has been cost, and it's typically over $100,000. Dynisco's Visco sensor is a new, small, affordable return stream online capillary rheometer that matches the capabilities of the higher-end units. We have compounders using it, as well as PET and polyolefin sheet and film extruders, high-end PET recyclers, and extruders of nylon shapes and rods. A maker of PET sheet for thermoform trays is using it as a viscosity and moisture analyzer, as they can monitor the IV number and quickly respond if dryers are not functioning adequately. Dynisco's Visco indicator is the lowest cost online system I'm aware of. How we designed this machine to closely match the results from a laboratory standard melt flow index test directly on the extruder is what I'm going to talk about today. This slide shows the Visco indicator rheological head on its stand. The Visco indicator has a small footprint for ease of setup and delivery. The rheological head is easy to install into the extruder because it can be connected using the same standard pressure process connection that Dynisco uses for its melt pressure transducer. The side stream of material that Visco indicator measures is not returned to the process stream. This type of rheometer is sometimes referred to as a bypass rheometer. My goal is to explain how the Visco indicator online rheometer duplicates the test conditions of the laboratory melt flow indexer or capillary rheometer. Melt viscosity measurements, such as melt flow index or MFI, are primary specifications of thermoplastic resins. MFI and melt viscosity are related to the polymer molecular properties, so these numbers give some measure of the physical properties of their product as well as the polymer processability. MFI is a measure of the ease of flow of the melt of a thermoplastic polymer. It is defined as the mass of polymer in grams extruded in 10 minutes using a specified test method, such as ASTM D1238 or ISO 1133. In the method, polymer is heated to a defined temperature, then it is driven through a capillary with a defined diameter and length by pressure created loading a piston with a defined weight. In the model above, the pressure in psi would be the pounds of the test load divided by the area of the piston in square inches. The weight of the material driven out of the capillary by that pressure in 10 minutes is that material's melt flow index, or MFI. The test is a very simple and efficient way to check material viscosity. Because of the short capillary L over D, this rheometer measures not only viscous losses in the capillary, but also viscoelastic losses in the capillary entrance. This means that the measurement is a function of both the rheometer geometry as well as the polymer viscosity. In other words, the ASTM D1238 standard defines both the apparatus and the polymer test conditions. Melt flow indexers must be hand-loaded with pellets and weights to create shear conditions, so the test requires a technician and it has to be done offline. The visco indicator simulates both the apparatus and test conditions of the melt flow index test right on an extruder. In the model of the visco indicator you can see on this slide, a side stream is taken from the extruder as indicated by the red text at the top center. Process pressure from the extruder forces polymer melt into a metering gear pump. The pump then generates the flow rate and pressure to extrude the polymer through a capillary. The temperature of the steel around the capillary and the pump is controlled, and a single pressure transducer is located above the capillary to measure driving pressure. The test polymer extrudes to atmosphere. By that I mean it falls to the floor, just like it would in the melt flow indexer. All material that enters the rheometer flows out as scrap, typically at the rate of 1/2 kilogram per hour. This rheometer duplicates the internal geometry of the melt flow indexer, so the capillary entrance effects are similar. In the ASTM mode of operation, the pressure defined by the load in the piston is specified in the ASTM method and created by controlling the gear pump flow rate using data from the pressure transducer. The material flow rate is calculated from the speed of the gear pump. A gear pump is essentially a positive displacement device that pumps the melt at a constant rate, regardless of the resistance to flow. By measuring the gear pump speed required to control pressure at the ASTM set point and knowing the pump flow rate, the visco indicator is able to calculate MFR directly as a function of pump RPM, given that the flow density is known. If you don't know the melt density for your polymer, you can easily measure it using a standard method on a melt flow indexer. This is how a visco indicator duplicates the test result from a melt flow indicator right on the extruder without needing a technician. Although the machine can control pump speed, enabling shear rate control, allowing viscosity measurements, we're going to talk about melt flow index testing. In direct MFR mode, pressure is controlled to the level that is equivalent to the weight used during the lab test. The pump speed required to maintain this pressure is the only variable in the equation that changes in real time, as you can see on the slide. Metering pump speed, pump flow rate, and flow density yield MFI directly as a function of pump RPM. In this bypass rheometer, the test polymer extrudes to atmosphere. As I said, it falls to the floor. This simple type of online rheometer very closely approximates the internal geometry of the plastometer and therefore the capillary entrance effects. You can see a factor in this equation that relates the diameter of the capillary used to the diameter of the ASTM die. You can also see a correlation factor in the equation that would enable the melt flow index to be adjusted to match that of a laboratory test. I'm going to now talk about this correlation. Before we discuss correlation, we have to make sure our machine is calibrated. The first thing to check is the calibration of the pressure and temperature sensors in the rheometer. Dynisco manufactures pressure and temperature sensors, so I could devote an entire presentation to their calibration, but I think most processors are comfortable dealing with these sensors, and Dynisco has other reference material available that covers this. The next major item to calibrate is the die. A mechanical inspection of the dimensions of the part to the specifications Dynisco provides is a straightforward way for most quality departments to check this. The next item to check is the weight of the extrudate. To check the weight calculation, observe what RPM the visco indicator pump is running at while running in MFI mode. Then set the machine up in speed mode and set the RPM to that value. Since this is a bypass rheometer, you can now make a time cut of the extrudate just as you would on a melt flow indexer and verify that the weight matches the expected value based on the pump volume and speed and the polymer density using the formula on the slide. To the extent that the weight is not right, either the pump volume or the polymer density parameters usually need to be adjusted because it is unlikely that the RPM measurement on the machine is off. Typically, it's usually the density that should be changed, but the pump is made from steel, so it is a wear item in abrasive or corrosive applications. Finally, you can cut up and run the actual extrudate from the rheometer back in the lab to see how well the MFIs match the online machine. Laboratory and online measurements do not always seem to agree. As a result, laboratory rheometers have been used to document final product viscosity or melt flow index, whereas online rheometers have been used more to measure process changes. The trend towards statistical process control requires a continuous measurement that only online rheometers can provide. Manufacturers must learn how to make online rheometry agree with the laboratory equipment. In the last slide, I proposed taking extrudate from the rheometer back to the lab for testing. This is a good idea because polymers may degrade as a function of their time temperature history, so you want to understand what the MFI of the actual material checked on the machine is for comparison purposes. If there is an issue with degradation for your polymer, you can work with Danesco to calculate the residence time of the specific machine configuration that has been proposed before finalizing the configuration. After you know your machine is good, and the material is good as well, the next thing to talk about is the fact that you're not running your production process at the melt flow index test temperature recommended by the ASTM standard, and melt flow index is a function of temperature. So the issue we have identified is that in real life, you aren't processing your polymer at the temperature the melt flow index testing is done at. The simplest solution to this problem is use the online rheometers to measure process changes and not worry about correlating to the lab. That said, in many applications, that is not acceptable. Maybe you're a recycler who wants to specify melt flow index to your customer, or maybe you simply want to continue to use the year's worth of process knowledge you've developed for your material based on laboratory melt flow index testing. To match the lab results, you could try to run the rheometer at the lab temperature. That may not be practical given the residence time required for the material to stabilize to lab temperature. Another solution is to add a correlation factor that is simply the ratio of the lab and online results. A lot of customers do this. The only downsides I see is that the correlation may need to be reset anytime the process temperature changes, and that it just feels wrong to me, like you simply added a fudge factor that makes a significant change to the reading just to make things work out. Another way to handle temperature issues is to make use of the Arrhenius relationship that polymers follow. The Arrhenius equation is a formula, an exponential relationship for the temperature dependence of reaction rates. The equation was first proposed by Arrhenius in 1889. The equation has a vast and important application in determining rate of chemical reactions and for the calculation of the energy of activation. Although Arrhenius provided a physical justification and interpretation of the formula, it's currently seen as an empirical relationship. It can be used to model the temperature variation of diffusion coefficients, the population of crystal vacancies, creep rates, and many other thermally induced processes. The Arrhenius equation has been applied to the rheological flow variables such as MFR. The key point for us to use this relationship is to determine the so-called activation energy for the material at the shear stress we're running the MFI test at. The way to use this is to take the natural logarithm of the equation on the previous slide and recognize that you can rearrange it in the same form as the equation of a line, y equals mx plus b, where y is the natural logarithm of mfi and x is the reciprocal of time. The slope of this line is related to the activation energy, as you can see from the formula. On this slide, I am showing how to calculate the activation energy. First, in the upper left-hand side of the slide, I asked one of our field service guys to take some LDPE we got from a recycler and run it in a melt flow indexer at various temperatures and record the MFI. He actually used this experiment to also train a brand new field service employee on how to run the indexer. So they ran the material at 190, 220, 250, 280, and 300 degrees Celsius. And at each temperature, they recorded the MFI readings, as you can see in the table. To the right of that table is the MFI and a standard fit to an exponential from Excel. In the bottom table, I converted the temperature to Kelvin as required by the Arrhenius equation and calculated the natural logarithm of MFI and 1 over T in columns 2 and 3. I then used the Excel slope function to calculate the slope of the line of columns 2 and 3. After that, I simply multiplied that slope times the value of the gas constant, R, times -1 to determine the activation energy. With a little further mathematical manipulation of the Arrhenius equation, you can rewrite it in a form that is useful to correct the MFI for temperature. In the formula above, the only variables are the process temperature the material is actually run at, the reference temperature of the ASTM test, the activation energy, EA, for the material, and the MFI actually measured by the rheometer. In the table above, we take the melt flow index measurements that vary from 0.852 at 190 C to over 6.5 at 300 C and apply the correction. We find the corrected MFI is the laboratory reading of 0.852 within about 1.5% over a temperature range greater than 100 C. Is that good enough? First, I would say that the melt index testing was done by an operator in training. Second, I would say that the actual material is 100% recycled. We don't know its history. And thirdly, I would say that the result is pretty good over a pretty wide range in temperature. Of course, this correction needs to be evaluated for your specific process and material, but I can say that we've had pretty good luck with this correlation. Now that we have correlated the online melt flow index reading to our lab results, I want to talk about how we can use this information to report an IV value. It is really useful to monitor the IV online rather than in the lab, especially since the IV test requires the use of solvents. Dynisco has developed software that provides excellent correlation of the standard capillary data to the intrinsic viscosity of PET. This feature has generated interest among PET compounders and processors. We do this on both laboratory melt flow indexers and online rheometers. The idea of this correlation is that both the zero shear rate melt viscosity and solution viscosity have been shown to be correlated to the molecular weight of the polymer. There is mathematics behind each of the correlations. The idea is that the equations are both related to the molecular weight, so they're related to each other. Danesco found the solutions to these equations, and Jim Riley, a former Danesco employee, published a paper on this topic at the time that we still distribute today. It is referenced on the slide and has all the details of his work. We have implemented this equation on our machines so they will report the IV of PET based on the melt flow rate at 285 C. So what we have done is talk about how to calibrate and set up an online rheometer to measure melt flow index. We've also discussed in detail how to correlate that reading to laboratory standard melt flow index using either a correlation coefficient or an Arrhenius relationship. We've also talked about how IV has been empirically correlated to MFI at 285 C. I went into these details to give you the confidence in the mathematics that has been implemented in our online rheometers. Armed with this, and the practical understanding of how to calibrate the machine, You can not only use the online rheometers to monitor process changes, you can also have the confidence in how the machine correlates its measurements to laboratory results. You might be saying to yourself that the title of this is Simplified Rheology, but that was a lot of math. On an actual VSCO indicator, there are a couple of setup screens that will allow you to enter the parameters we discussed utilizing existing terminology that your operators are already familiar with. For instance, you can set up the pressure control value by simply entering the test load from your laboratory melt flow index test. We have simple methods to determine each of the parameters, and we can walk you through the process as you set up your system. The VSCO indicator has a Windows 10 IoT or Internet of Things based rheological software platform that leverages the power of Windows 10. IoT devices running Windows 10 can make use of many other Microsoft services for a better user experience and control. Windows 10 IoT provides an interface that's familiar to almost everyone. Operators will find this much more intuitive than some of the PLC ladder logic based interfaces. They can navigate around, set up, and do things that would prove difficult or confusing on other platforms. It also has the advantage of being easy to set up on a Windows-based network. Since VSCO Indicator is Windows-based, the basic setup is the same as that of all other devices on the network. In addition, VSCO Indicator allows you to collect and store process data to internal or external storage. As you can see on the slide, the VSCO Indicator has the look and feel that will be familiar to most shop floor personnel. Why is this important? It lowers the training time to become effective in measuring the rheological properties of your polymer process. With this, Bill DeRosius will now go through how we have made it the connection to the extruder simple.
Thanks, John. We have discussed how the VSCO indicator and Windows 10 IoT control have made the use and interpretation of rheological data easy to use. I'm going to show a couple of slides that will show how Danesco has made the installation of our VSCO indicator simple as well. Historically, installing an online rheometer requires special process connections, dedicated wire runs. While in traditional polymer processing facilities this is necessary due to hazardous environment requirements, it came at a price point and complexity that the average processor just could not justify. Today, with the new VSCO indicator, we have removed all the barriers to this adoption. The best location for measuring online rheology is before the die on an extruder. In the application shown, this customer has a tight window in between the screen changer and the underwater pelletizer. He did have an existing auxiliary temperature sensor located there with a half 20 connection. This is shown in the blue square in the middle. This port is quite common in the extrusion industry with pressure and temperature sensors as well as rupture burst plugs. By utilizing this port, it eliminates the need to modify the extruder and was already in the proper location to get the best reading for the finished polymer's rheology. The areas that we had to overcome was that the port was located at a negative 15-degree angle from the 9 o'clock position, and as shown in the pictures to the left and right, the real estate that we had to work with was quite tight. While visiting a number of extrusion facilities, we found that most existing ports that we could use were in less than ideal spots. To correct this, we developed a series of heated process adapters that are available to meet a variety of angles. These are designed in such a way that they divert the stream not only in a variety of angles, but the tube itself can also rotate before it's locked down. This adjustability allows us to adapt to most locations without specially designed adapters. One thing to note is that after the material passes through the rheometer and is evaluated, a small discharge stream less than a half kilogram an hour is dropped into a purge bucket beneath the unit. In this case, it happened to coincide with the same purge bucket that was underneath the underwater pelletizer connection. We developed the VSCO indicator to have an easy mount stand and cable set that is a single one-plug 240-volt single-phase connection. This connection requires a quick and easy installation plan without costly specialized wiring. In a standard form, the unit can roll right up to the extruder. In the case of our application that we were referring to earlier, we could not just roll up the stand to the port. We simply did not have the room. What we're able to do using the components of our standard aluminum stand kit, we developed a custom stand that clamped to the pelletizer base that allowed for adjustment in the vertical, horizontal, and lateral positions. We also used the main support structure as a rolling stand for the control unit in the HMI touchscreen. By using these type of components and a bit of forethought, the unit can be installed in most existing applications. By providing the information on this slide, Dynisco can assist in adapting an online VSCO indicator to your process providing the valuable polymer specifications that will allow you to have the confidence in the material you are using to make your final product. I would like to thank you for your valuable time. This concludes today's presentation. We're now going to open up the floor to questions.
Okay, now it's time for the Q&A portion of the webinar. Okay, our first question is, if I use the Arrhenius correlation factor you talked about, can I still use the correlation factor you mentioned?
I'll take that question. It's John Kazadi. Absolutely, both corrections can be used. The Arrhenius relationship is intended to allow you to run your process at a different temperature than your standard temperature that you used in your ASTM laboratory test, while getting the same melt flow rate. You can still use the correlation factor, though, to make the reading from the rheometer match that of your laboratory standard. But we recommend following the calibration steps I outlined during the presentation beforehand. We want to know the machine is fully calibrated and the material is good before making any further adjustments.
Thank you. Our next question is, LD is same for all polymers, or is there specifically defined based on material?
I assume you mean the L over D, the ratio in the orifice. Typically, when we're doing a melt flow index test, we intend to match the L over D used in the LMI, short die of 3.8. In some viscosity tests or in other applications, we can make dies of other lengths as well.
Thank you. Our next question is, can I enter all test loads into the Visco indicator? And if not, what do I need to be aware of?
I assume you mean the weights, the test loads that we're using in the laboratory test. You can enter those weights into our machine. If you run multiple different materials or setups, you can set up the test load for each recipe. You're allowed to create recipes for each material. And then you can simply change the recipe. If by running different test loads you meant, can I run a method D test where I change the test load, then yes, it's possible in certain versions of the machine, certain versions of the software. You may need a software update for a machine you already have, but we have that capability.
Thank you. How many tests should I do on my melt flow indexer to obtain an accurate correlation factor for temperature variations?
In the presentation, we fit the data to a line, so in theory, only 2 points are required. We would recommend an average melt flow index be determined over multiple tests at least 2 different temperatures. I would recommend doing more than 2, though, so you can check the accuracy of the fit.
Next question. How do you prepare the samples to determine the intrinsic viscosity, which is what you recommend?
We are doing a correlation to a measurement that would be done on using solution viscosity. So we're running them on a melt flow indexer with the same preparation that we would do during any melt flow rate test. Certainly, you may need to dry materials as you would with any. I'm not sure under preparation where we'd be going beyond that.
Okay, our next question. Are there any specific materials that do not work well with the viscose indicator?
I'm thinking about that. That's you didn't lose your mic there. Certainly, there are foams that we don't have a lot of experience with. There are. We use the Visco indicator in applications actually that aren't plastics. We've used it in certain foods. Yeah, if you have a specific instance, please contact the experts at Dynisco and we can work through that if you have a specific material that you're thinking about.
Okay, the next question is, what is the maximum admissible pressure?
We offer a range of pressure transducers. If you're setting it up as a standard melt flow index, we typically use a low pressure transducer, often a 250 psi transducer inside of it. So if it's configured in that fashion, the maximum pressure is limited by which pressure sensor you have installed. Those can be substituted, but you may be limited by the sensor. If you're not limited by the sensor, it's approximately 4,000 psi, where the gear pump is limiting us. So it depends upon the specific configuration. I would say overall, the machine is limited to approximately 4,000 psi.
Our next question is, how much room do I need around the VSCO indicator to allow for maintenance and cleaning?
Okay, around the VSCO indicator, it doesn't require a tremendous amount of room, but what it does need is you do need to have access to the front of the VSCO indicator just to be able to purge the line as it's coming into the unit, as well as making sure you can address capillary and adjustments to the capillary if you're changing different materials. So you don't need a lot of room, but you do need to probably within a foot or two around the instrument to be able to access those two points to be able to maintain the machine.
Our next question is, obviously temperature is a very important variable in melt index measurement. What actually occurs if the material is too hot when it enters the VSCO indicator?
That would depend upon the residence time within the VSCO indicator itself, which is a calculation that we can make. We need to balance the residence time of the VSCO indicator to the degradation of the material. It would be material dependent. If the material is operating in a temperature range where it's not degrading as a function of temperature, again, a test we could do on a melt flow indexer, you could certainly run at a low speed with a specific die. We could design it so that it has enough residence time that it comes to the proper temperature. If you want to run the VSCO indicator at a different temperature than your process temperature. But this would really be one where you want to talk about a specific application or configuration with Dynisco before the configuration of the machine is complete.
Okay. In your installation example, you displayed a special configuration for the stand. How easy is it the stand to modify?
Actually, the stand is quite easy to modify. In most applications, you will see the customer actually have the vertical portion of the stand on rolling casters. That'll handle the control unit and the HMI. But we can also modify the other pieces of the stand. They're typical aluminum extrusions. You can use a saw or a circular saw with an aluminum blade that you can cut it down to whatever size and configuration you're looking for. We also offer a small toolkit that can drill the correct holes for the locking hardware so you can make sure that everything locks together as it should. So it's quite easy to modify for specific needs.
Okay, our next question. Is the VSCO indicator designed to correlate to virgin material or the finished product?
The VSCO indicator is intended to correlate to the material that's extruding from the machine, not the incoming material.
Okay, next question. Can we adapt the VSCO indicator to process ports other than a standard pressure transducer 1/220?
We can actually make a lot of different connections. The 1/220 port is quite common on most extruders, but we can also adapt to any other process connection that happens to exist, and we have done that in many applications.
Okay, next question. What do you suggest for a PET regrinder, the LCR or VSCO indicator?
Well, it really depends on what that PET plant is doing. If he's doing lab experiments to make sure the material is good quality, they're going to use a lab instrument, whether it's a melt flow indexer or a capillariometer. But while he's running that material to either increase the IV or to make another product, the visco indicator is a perfect complement to that line, where you can verify what you had in your lab and then increase it to what your end product you want it to be.
Okay. Next question. What's the exact correlation of the measurement of the LMI with the results of IV?
That is something that you'd want to test in your laboratory with your machine. There is that is a empirical correlation that you'd want to verify. We don't provide a precise specification for the correlation, but we can provide what we've done on our machine and how well that's worked for us.
Okay, we're going to wrap up the webinar right there. Thank you to our presenters and for spending some time with us today. And thank you to all our audience members for being part of this webinar event. Thank you very much, and take care. We'll talk soon.